Hello everyone, welcome to our class. Today we will talk about signal. So what's a signal? And how would you signal to communicate between the process? So this is the idea, the first inter-process communication we have to support the process communication. So let's start today's class. So we know we have a kernel, we have a couple different process one, process two. We also have a shell to deal with the user input. When you type something, the shell will transfer, like a transfer interpreter, uh, the message you type and try to figure out what the command should go. So you can imagine that the shell is also a process, right? So if you want to use a shell to control particular each one process, how you use it to control it. If you have one process want to talk to another process, how to do it? You know, the process, they are independent to each other. So without a kernel, you cannot talk to each other. So you can imagine that everything we try to communicate, we will use kernel to support this. So this is the idea about the inter-process communication. So there's a couple ways to support this inter-process communication. You can use pipe, you can use socket, you can use signal. And signal is the first one we covered in this course. So how to use signal to talk to other process, okay? So the basic idea of the signal is that we try to share information. We try to say, okay, today is Moon Festival. Today is New Year. So this kind of information from your kernel to send to other process. Okay, so for example, our kernel can tell the process one, okay, today is New Year, the first day of your new year. Okay, so when kernel tell this information to a process, the process can do some reaction based on what the message is sent to from the kernel to process one, right? So if your process two want to send the same information, for example, I want to tell the process one is that today is the new year, you just tell the kernel about this. Hey, God, hey, kernel, can you send this message to the process one for me? You can do something like that. Okay, so you can imagine that this is kind of an event. So signal is event. Signal is event in your systems. So the kernel treats it as an event. So which means it's predetermined. So this is predetermined. So why it's predetermined? Because, for example, the event New Year's is just like the common the common sense event for every process, right? So for every whole world, right? So everyone knows. Okay, so today is New Year. What's the New Year means? Everyone knows it. Everyone knows this. So this is predetermined like a holiday or predetermined the day before everyone. So it's everyone has a common sense of this New Year event. So again, if kernel want to send a signal to a process, the signal is predetermined. So which means you only have a limited number of the signal you can use. For example, for process two, you can say, okay, kernel, could you send the signal one to a process one for me? The kernel definitely say, yes, I can do it. But you cannot say, you cannot ask the kernel to do something like, kernel, I want to send a signal, the signal code X, Y, Z, T, E, W, and this is totally like a long number, just like a randomized number made by your process two. Then the kernel will say, no, I don't know what the signal is, because this is not predetermined. So the signal is predetermined. So you can treat this as an event. Every process, every system know what this means because the signal number is predetermined. For example, I see the signal number, let's say 2, this particular signal number 2. When I see this 2, I know, okay, this signal means something, means what? for example, means interrupt or means like a child process finish. So you can use this information to know what happened. Okay, so sensing happened for your user. If you want to like remove, for example, we usually like when we run a program and it's got the infinite loop, we say control control C. We type control C, we try to terminate it, the program. The control C, when you type it, your shell will deal with this control C, do some process, and send the kernel say, please interrupt. Please interrupt process. One. Okay, so it will transfer the message from your control C and send as kernel to send a signal. So the kernel will send a signal, okay, I want to interrupt. I said the kernel send the interrupt signal to a process. So the process one, when it see the interrupt, it says, okay, right now I need to terminate it. Right now I need to stop because I received this interrupt. So this is the idea about a sending signal. Of course, you can use another process, for example, the process process 2 to interrupt, send an interrupt signal to here. So you can also use one process to send interrupt signal to another process to interrupt another process, to terminate another process. So this is the idea of the inter-process communication. So actually, does it really has a real like communication? No, they cannot send like a random message. For example, I want to send some data to you and I expect you respond to me to a data. No, it's not. It's more like I send a message to you and let you know something happened. And based on what thing happens, you can follow it. You can try to, for example, when I see a New Year, I can say Happy New Year. So when your process one receive a message, today is New Year, it's just response, Happy New Year, finish. So if a process one receive interrupt, it's just terminated. Okay, so this is the basic idea of the signal as an inter-process communication. However, sometimes when you run some process, you don't want to get the stop or get like a suspend, get the interrupt, right? For example, today is New Year, but I don't care. I don't care New Year. So when you say, "Hey, today is New Year," I don't want to say Happy New Year. I just ignore it. Don't bother me. I don't want to. I don't care it. So in this case, how you process like ignore the signal. So actually, you can do this, but how to do it? You can try to have some like mask stuff. So this mask can mask the signal. Okay. So if you have some interrupt here, and this interrupt got to mask by this process, then the process will ignore the signal. Not every signal can be ignored. Some signals are really important. For example, the system has some problem, some issues, and your process cannot continue. You have to stop because there's some issues happen. In this case, the signal cannot be blocked. But for some interrupt, it's okay. If, for example, the process 2 want to like interrupt process 1 by sending a signal for interrupt SIGINT, then your process 1 can ignore it. So this is called mask, signal mask. Okay, so how the signal mask works? Let's see the next slides. Okay, so actually you can imagine that in your process, inside each process, you have this not array. Actually, this is not array, but you can treat it as array. But again, this is not array. It's just each element here is just one bit. So it's actually just one sequence of a bit. So you can treat it as a sequence of bit. It's not array. Again, it's not array, but you can imagine it's like an array. Okay, so each process have a pending array, not array, pending bits, bit set, and block bit set. So for example, if I have a signal from your CPU, say, okay, so something happened, I need to stop. So in this case, the CPU definitely will send this message to a kernel because kernel try to manage everything, including the communication between each process to the hardware stuff. Okay, so the kernel know something happened. It can try to interrupt it. So if we try to interrupt it, the only thing happen is what's happened. The kernel will change this bit to very bit. If this is to present the interrupt, if this is for interrupt, it will change this bit from 0 to 1. Okay, so because when you do something for your kernel, this is going to sleep, right? Imagine that if you have only one core CPU, just one CPU, one core, which means only one process can be run. So if you run the kernel process, you cannot run process one. So actually this is on sleep. So when the process one is sleep, you try to change the value in this kind of array. Actually, it's a vector, the bit vector. Then when the process wake up, the process will check the pending bit first. So if the process see, okay, this is 1, then I should stop. So this is a process. This is what like the step-by-step process between how to send the signal to your process. So you send a signal? No, it's not sending a signal. It's more like I try to overwrite. I try to replace your bit vector. And I change your bit vector to cause you to stop when you wake up. When the process wake up, it will stop because it will check the pending vector bit first. Okay, so if you know something like this, we can also do a different concept. For example, I have a kernel try to do the signal, like try to send the sig int. This is the sig interrupt, and for this one, it changed to 1. And before the kernel wake up this, so this still asleep. Okay, before the kernel wake up it, the process 2 run first. Then the process 2 send another signal. Let's do another color. The process 2 try to send a signal. It's try to ask the kernel send another signal to the process 1, and it's the same sig integer. Okay, so this is the process 2. So the process 2 going to sleep. The kernel will check. Okay, the kernel find this. So it's sending the sig interrupt again to the process 1. So when the process 1 before the process 1 wake up, actually the kernel do this again, means it will replace the number here to 1. So it's not increase the number. Each number here, each element here is just 1 bit. Can be 0 or 1. So you cannot have a 2 here. You cannot have 2 here. So no matter how many signal sent to the process, before the process wake up, the signal is always just like replace the bit vector. So which means when you got the process 1 wake up, it will check this number and it will find, okay, I got sig interrupt. But how many sig interrupt sent to me? The process doesn't know. The process only know there's only 1 value here, and which means that this is the event I should do. This is something I should like respond. Imagine that you have a friend, friend 1 tell you this is New York, but before you respond to it, another friend tell you this is New York. Do you say Happy New York twice? No, you just say Happy New York, right? So no matter how many number of signals comes in, if the signal is the same, the process won't aware of it. The process only check the vector bit, like a vector bit. If it's 1, means something happened. If it's 0, means nothing there. Okay, so this is the idea of the signal communication. So again, we can do a more complicated case is use a mask. So actually, this is a mask bit like a vector. So what's a mask? If we try to change, for example, the process 1, it is one want to ignore. It is one want to ignore the sig interrupt. Okay, if the process one wants to ignore the signal interrupt, in this case, your process two sends sig interrupt, try to uh, interrupt the process one. So your kernel go here and try to like send the signal interrupt one, interrupt to process one. Of course, the process one is on sleep, so the kernel try to change the sig interrupt here to one. Okay, before the process one wake up. Okay, so right now the process one wake up. Right now, process one wake up. The process will check this. The process will check. Okay, I receive a signal, but I also mask this signal. So this is match. So actually, if you have a sequence of a bit vector, you have the same number of bit vector as a mask. So if they are matches, your process will ignore it because I already choose to block it. You still try to give this, doesn't mean anything. So I can ignore it. This is how you use your mask to block the signal. Because if you set the special bit here before your process actually do something, when it wake up, it will check the pending signal first. Then if it find the one, the value, it will use to compare the block vector, which means if they are matched to each other, so like 1 to 1, then nothing happens. So you can do some like a computation to like simplify these bits, these like a bit like operations. So actually, there's some bit operations can be used to simplify this process, but I'm not going to too much detail about it. Okay, so this is the idea. So the idea is you have a special, you can treat it as an array, but actually it's a vector, bit vector. And if you want to send any signal to it, actually the kernel just change your value inside a vector. Before you receive any signal, you can also try to change your block, your mask, to avoid to ignore the signal sent to you. So if the number they match to each other, then of course your block, your mask can ignore the signal, and you don't need to be bothered by these signals. Okay. Joe, I have a question. If I don't use the signal mask, does the process always be terminated when receive a signal? Uh, if it's always be terminated when receive a signal, why we need so many signals to be defined? Okay, so this is a good question. So actually, when a process receives a signal, based on different signal, the process has a different default action to respond to different signal. For example, when you receive a happy birthday, you will reply, okay, thanks for like celebrating my birthday, right? When you receive a Happy New Year, you will respond like, okay, Happy New Year. When you receive some like signal you want to ignore, you probably just ignore it. So actually, there's a different default action for each signal. So now they are not the same. So I'm going to talk about what's the action you have for each signal. So when your kernel sends a signal to your process, this process can have a mask, to support. But if you just put like every bit in the mask as 0, which means you don't care, not don't care, you care every signal. If you care every signal, what's the default action for each one? So actually, there's a different default actions. The first one is called ignore. So actually, just do nothing by default. When your process receives the signal, even you don't do any block, it will be ignored. The signal will be ignored. Okay. Another one is terminated, which means the code should be the program should be terminated. For example, we try to use Control C by user to terminate the program, and when a program receives a sig interrupt, it will terminate it by default. If you don't block it, it will be terminated by default. Another one we call is core dump, which means it's very similar to terminated because it also will be terminated. But before it's terminated, it will try to generate some report for the programmer or user to export what happened, what the error might be. So actually they are similar, but the core dump will generate some reports before you actually terminate it. Another one is kind of stop. The stop is just suspend. It's not be terminated, okay? So it's just like a go to sleep. Just like, oh, I go to sleep until some other process use signal to wake me up. So it's just got to suspend, but the process is still there. It's still in the system. So which means you have another signal called resume. So some signal is used to make a process wake up. So if the process got suspended, got stopped, you can use other signal to wake up the process. So actually, this is the default actions you can have to support the different signal situations. Okay, so but remember, not every signal can be masked, can be like blocked. Not every signal can be blocked. Some signal by default action, they are really, really important because your process have to be terminated. For example, what's the situation? If you try to divide by 0, and if your kernel allow you to continue to compute something, it might like make your system broken, right? Because you can never like do divide by 0, and you can still use this infinite like a loop, infinite number to compute. So this is like one example you probably will got like terminated. And another one is like a kill. If you have really terrible like situation, the kernel decide to like remove this process because this process try to access some like a really critical data and try to like mess up the server maybe. In this case, your server have something like a sick kill. So actually you can have special, this is very, very important. This is very important signal. It's called sick kill. The sick kill the signal cannot be blocked. Cannot be blocked, cannot be ignored, cannot be handled. We will talk about the handler in other video. So actually you can try to collect, just very, very similar in Java, you try to throw exception, you try to catch an exception. So of course, in C process, they have some way to like catch the signal and handle it. So even for this handler, the CKL cannot be handled. So because it's so important, if you try to kill a process, it means this process has some issue and it should be killed. So this kind of signal cannot be blocked, cannot be ignored, cannot be handled. Okay, so if you are interested to what signal is very, very like dangerous, what signal is not, please review the slides. We list a couple important signals in the slides, so please review it. Okay, so here's couple important signal you might see in this lecture. Sick child will be sent when your child process is terminated. So why we got zombie process? Actually, it's related to this signal. The sick child will be sent when the child process is finished. Also, if you have something like a divide by 0 arrow message, let's seek floating pointer arrow, the seek FPE, the signal will be sent. The seek segmental, very popular one, right? Because you got segmental 4 because of it. If you got segmental 4 means your process received the signal. And seek kill is very, very important one. Seek kill cannot be called, cannot be ignored, cannot be handled. So keep in mind, not every signal can be handled, okay? Okay, so this is for today. Today we talk about what's a signal, and signal as the first inter-process communication component, IPC, in this class. We can let you know it's actually an easy way for you to like send a message from one process to another process or from your kernel to a process. The signal can be blocked. Can be blocked by like set up the mask like your signal mask. And actually how this works is all about a big vector. So that's a 2 big vector inside your process to handle the signal receiving or signal block. And if you don't like handle the signals, your process will have some different response to each different signal. Some response will be just ignore, just like you don't care. Some response will be, okay, I just go to sleep. Some response will be, oh, I have to be finished. Okay, because some like important signal just send here means I probably like made something wrong, so I need to sleep. I need to like be killed. I need to be terminated. Okay, so because some signals are really important, so they cannot be handled or ignored. So just keep in mind that it's a little bit like a lot of different like situation or default action for each signal. And if you want to know what's the default action for particular signal, go to check the list. We give you like go to check the signal list in the lecture. Okay, so I hope you enjoyed today's video. I hope you understand what the signal is. And we will talk about a little bit about how to program the signal stuff in other videos. So see you next time. Signal is awesome.